It is 2 a.m., and a child is lying on a rooftop, staring up at the sky. He can't see the sun because it's nighttime, but he knows the sun is still there, somewhere beneath him. He thinks that if he could sit in a rocket and point it straight downward, he would eventually reach the sun. It seems like a simple idea. But there is one thing that child doesn't know, and it's something the world's greatest scientists have been trying to understand for the last 60 years. Reaching a point directly above or below the sun is actually the most difficult journey in the entire solar system. It is so difficult that even though we have reached Pluto 3.5 billion miles away, no human or robotic spacecraft has ever managed to position itself directly above the sun and capture a photograph looking down. And do you know the most surprising part of this entire story? To go up, you first have to fall down, straight toward the sun. Then, just as you're about to burn up, you have to fire the engines. And just a year ago, in March 2025, for the first time in human history, we caught a glimpse of a place that scientists themselves call Terra Incognita, meaning a land with no map. Today, we're going to understand this entire story from beginning to end. And before we continue, if you haven't subscribed to the channel yet, take a second to subscribe and turn on the notification bell so you don't miss any future videos. Now, let's dive straight in. Just like that child, most of us think that if the sun is above us, then all we have to do is travel upward. But real physics works very differently. To understand why, we need to look at something we experience every single day without even noticing it. Right now, wherever you're listening from, you're not actually standing still. You're moving. The entire Earth is racing around the sun at a speed of about 30 kilometers per second, and you're moving along with it. That means this planet travels about 30 kilometers forward every single second, or roughly 67,000 miles per hour. You don't feel that motion because everything around you is moving together, and every rocket launched from Earth inherits that entire speed for free. When a SpaceX rocket lifts off, it doesn't begin from a standstill. It is already racing around the sun at 30 kilometers per second, just like the rest of us, and that's an incredible advantage. If we want to travel to Mars, that existing sideways motion does most of the work for us. All we need is a small adjustment, a little extra speed, in exactly the right direction, and we're on our way to Mars. That's one of the reasons we can reach other planets relatively easily. But now, let's come back to that child's question. What happens when you don't want to travel toward Mars, but instead want to go straight up, completely out of the flat plane where all the planets orbit the sun? Suddenly, that same sideways motion, which had been helping you all along, becomes your greatest obstacle. To travel straight up, you first have to cancel out the 30 kilometers per second of sideways speed you already have, and only then can you begin accelerating in a new direction. The amount of energy required is almost unbelievable. To reach Mars, you only need about 4 kilometers per second of additional speed, but to head straight above the sun's orbital plane, you need around 30 kilometers per second, about 10 times more. Think about what that really means. Reaching Pluto, 3.5 billion miles away, requires less energy than reaching a point only a few million miles above the sun. A relatively short journey upward is so demanding that crossing the entire solar system actually becomes the easier trip. This is the prison we're trapped inside. Earth's orbital motion gives us tremendous speed for free in one direction, but it also surrounds us like an invisible wall in every other direction. We can travel comfortably around the sun. We can visit every planet that shares the same orbital plane. But the moment we try to leave that plane, we have to fight against 4.5 billion years of orbital momentum all at once. And this is exactly why the sun's poles remain one of the last great frontiers in astronomy and unexplored boundary. Just stop and think about it. We have detailed maps of Mars. We have high-resolution images of Pluto. We have close-up views of comets. But the poles of our own sun, the closest star to Earth, were only photographed properly a few months ago. The same star that rises every morning, the one that is lit every day of our lives until recently, no one had ever seen what existed above its poles. And this matters far more than it might seem. because the sun's polar regions are where some of its most powerful and most important activity takes place. The fastest solar winds originate there. Every 11 years, the sun's magnetic field flips, with the north becoming south and the south becoming north, and that entire process begins at the poles. The space weather that affects our entire solar system depends on what happens above and below the sun, yet for centuries we have only observed it from the side. It's like trying to understand Earth's entire climate while standing only at the equator. You would never discover the ice, the storms, or the completely different world that exists at the poles. So far, only 2 missions have managed to capture a true polar view of the sun, and the first one was so ingenious that it almost sounds unbelievable. Back in 1990, NASA and ESA launched a spacecraft called Ulysses. Its mission was to study the sun's poles. But the challenge was the same as always. How do you escape the plane in which the planets orbit? The scientists came up with a remarkable solution. Instead of sending Ulysses straight upward, they first sent it toward Jupiter. In other words, they deliberately sent it in the opposite direction, farther away from the sun. Then, as Ulysses flew past Jupiter, the planet's enormous gravity acted like a slingshot, flinging the spacecraft upward at an angle of nearly 80 degrees. From that new angle, it began falling back toward the sun, and this time it entered a tilted orbit that allowed it to pass over the sun's poles. Ulysses gave us the first direct measurements of the powerful solar winds flowing from the sun's polar regions. But there was one major limitation. It had been designed during the 1980s. Its instruments reflected the technology of that era, and it carried no camera capable of photographing the poles. We learned what conditions were like there, but we never actually saw them with our own eyes. The second mission is taking place right now. It is an ESA spacecraft called Solar Orbiter, launched in 2020. By repeatedly using the gravity of Venus, it has spent years slowly tilting its orbit, leaning a little farther with every journey around the sun. Then, in March 2025, something happened that had never happened before. Solar Orbiter transmitted the first direct images in human history of the sun's south pole. Think about that for a moment. For thousands of years of human civilization, billions of people have looked at the sun. They honored it. They depended on it. They lived their entire lives beneath its light. But no one had ever seen what its poles actually looked like. During a press conference, ESA Science Director Carol Mandel said something that still resonates today. Today, we are showing humanity the sun's pole for the first time. And Sami Solanki, the scientist leading the camera team, spoke what may be the most memorable words in this entire story. He said, "The sun's poles are truly terra incognita," meaning an unknown land with no map and no record. And what did those images reveal? A magnetically tangled, chaotic region, completely different from the smooth, glowing surface we see from Earth. It looked as though thousands of powerful magnets had been woven together, all twisting and vibrating at the same time. A hidden world unlike anything we had imagined, existing on the surface of our nearest star, yet remaining completely unseen until now. But the sun's poles are not the only reason scientists want to travel above the plane of the solar system. There is an even greater reason, and it is even more astonishing. We still don't know what our own solar system looks like from the outside. Surrounding the sun is an enormous bubble that scientists call the heliosphere. This is the vast region where the sun's solar wind dominates, pushing back the interstellar material beyond it. Every planet, every comet, and every one of us exists inside this enormous bubble. Beyond it lies the deep environment of our galaxy, filled with cosmic rays that the heliosphere helps shield us from. For decades, scientists believed this bubble looked like a comet, with a rounded front and a long tail stretching behind it. That was the picture shown in textbooks. It was the illustration you would find almost everywhere you looked, even today. But in 2020, a scientist at Boston University named Mira Ophir developed a new computer model using NASA data, and the results surprised everyone. According to her model, the heliosphere doesn't resemble a comet at all. Instead, it looks more like a flattened croissant. a compressed shape with a curved center and two smaller lobes extending from the sides. And the most surprising part is that there may not be a long tail at all. If that's true, then our cosmic home, the region of space we have lived in and pictured in textbooks for decades, may not be shaped the way we always believed. And why can't we say this with complete confidence? Because we have never seen our own bubble from the outside. The Voyager spacecraft traveled beyond its boundary, but both missions left the solar system while remaining close to the same flat plane where the planets orbit. Their discoveries were extraordinary, but their perspective was limited. Right now, NASA has a mission working to answer this mystery. It is called IMAP, the Interstellar Mapping and Acceleration Probe. It launched in September 2025, reached its operational position in January 2026, and is now mapping the boundary of our solar bubble from the inside. But there is only one way to discover its true shape with certainty: travel above the plane of the solar system and look back down. That is a view no spacecraft has ever witnessed. So now comes the biggest question. How do we solve this problem of escaping vertically from the solar system's orbital plane? The answer isn't simply to build a bigger rocket. No practical rocket can carry enough fuel to cancel out Earth's orbital speed of 30 kilometers per second. The numbers just don't work. But there is another solution, and it is so counterintuitive that it almost sounds impossible. It's called the Solar Oberth Maneuver. The entire idea turns our intuition upside down. Instead of pointing the rocket upward, you do the exact opposite. You send the spacecraft falling inward, straight toward the blazing sun, and you let gravity do the work. As it dives deeper, the sun's gravity accelerates it more and more, just like a stone falling into a deep canyon. By the time it reaches its closest point to the sun, its speed has climbed to hundreds of kilometers per second, possibly well over 100. Then, at the exact moment when it is closest to the sun, just before the intense heat becomes overwhelming, you ignite the engine. Why? Because back in 1929, a scientist named Hermann Oberth described a remarkable principle. A rocket burn becomes far more effective when it happens at extremely high speed, deep inside a strong gravitational field. Use the same amount of fuel, but burn it at the point closest to the sun, and you gain dramatically more energy. In other words, that terrifying dive becomes your real launch pad. The small amount of fuel carried from Earth is transformed into an enormous burst of energy, allowing the spacecraft to leave the orbital plane and finally climb straight toward the sun's poles. There is another possible solution as well: solar sails. It is one of the most elegant ideas ever proposed. Imagine unfolding a gigantic, shimmering sheet, thousands of square meters in size, so thin that it is almost transparent. As the spacecraft travels through space, sunlight itself, carried by countless tiny photons, continuously pushes against that sail. No fuel, no engines, just light. Year after year, that gentle pressure slowly changes the spacecraft's orbit, gradually tilting it farther and farther away from the plane of the planets. It could take years to reach a polar orbit, but the sail never runs out of fuel. It only needs sunlight, and perhaps the real solution will combine both ideas. A spacecraft could slowly spiral closer and closer to the sun using a solar sail, then, at its closest approach, perform a solar Oberth maneuver to launch itself upward, and finally continue its journey toward the poles with nothing but the steady pressure of sunlight. Now imagine that one day we actually succeed. What would a spacecraft see from above? The very first thing that would change is the view itself. The ecliptic plane, the flat region where all the planets orbit and where we live, is far from empty. It is filled with an extremely thin cloud of dust, created by billions of years of collisions between comets and asteroids. In fact, you can sometimes see evidence of that dust with your own eyes. On a very dark evening, shortly after sunset, a faint triangular glow may rise from the horizon. That gentle glow is called zodiacal light. It is simply sunlight reflecting from the countless tiny particles of dust spread throughout the plane of our solar system. But a spacecraft that climbed above this plane would leave that cloud of dust behind in just a few months, and the view from there would be unbelievably clear. No haze, no scattered light. From that vantage point, a telescope could detect faint signals that are normally hidden by the dust within the plane of the solar system. If we want to search for signs of life around other stars, this could become one of the best places to do it. And perhaps most importantly, from that height, we would finally see our solar system in its true form. All the planets would appear as part of a single flat disk, a thin ring of dust surrounding the Sun, enclosed within the vast heliosphere, whatever its true shape ultimately turns out to be. For the first time, we would be able to look back at our own home from the outside, just as astronauts once looked back at Earth from orbit, forever changing the way humanity saw itself. And this is the one picture that is still missing today. We have captured millions of images of the universe's distant galaxies, black holes, nebulae, and countless other wonders. But a photograph of our own solar system seen from above, from the outside, has never been taken. Not a single human being or robotic spacecraft has ever sent us that image. Now think back to the story I told you at the beginning, about the child lying on the rooftop, believing that reaching the sun would be easy. Just point the rocket upward and go. Now you know that he wasn't really wrong. His reasoning made perfect sense. He simply didn't know that the universe has built an incredibly clever prison around us. A prison where we can travel almost anywhere with surprising ease, but not in every direction. The one direction that seems simplest is the one that hides some of the greatest answers. And maybe that's the most beautiful part of this entire story. The most overlooked and mysterious place in our cosmic neighborhood isn't hidden in some distant galaxy. It's right above our own sun. It has been there every day and every night, just beyond our view. And now, after more than 60 years of effort, we are finally beginning to find a way to reach it. Before we finish, I'd love to know what you think. If you had the chance to design the very first mission to travel straight above the sun, which approach would you choose? The slow, patient journey powered by a solar sail, or the dramatic solar orbit maneuver, diving toward the sun and igniting the engine at the very last moment? Think about it for a moment and let me know. I hope you learned something new today. If you enjoyed listening, don't forget to like this video. Share it with someone who loves space. And if you're new here, subscribe and turn on the notification bell so you don't miss future videos. Thanks for listening, and I'll see you in the next one.